Yes, in today class actually we are going to deal about the strain gauge problem as well as the different types of strain gauges. Okay, so the different types of strain gauges you all know in the previous class. The working principle of strain gauge we have talked about, that is nothing but R, which is nothing but rho L divided by A. This is the working principle of your strain gauge, that is nothing but if a metal conductor is getting into stressed, I mean there is a change in dimension, then there will be a change in resistivity property. So strain gauge which comes under the resistive type of transducers. Okay, and not only that, this will also act like a primary as well as secondary transducer. So the different types of your strain gauges are unbonded metal strain gauge, bonded metal strain gauge, bonded metal foil strain gauge, vacuum deposited thin metal film, then bonded semiconductor, then diffused metal strain gauge. Out of these types, actually the used one, that is like in research point of view, the people are used to go for bonded semiconductor metal strain gauge because of the sensitivity, resolution as well as good gauge factor. Okay, so here actually we are going to see about some of the problems in the class. So the first problem is about the gauge factor is given, and in the problem they have indicated that you can neglect piezoresistive effects and you are supposed to calculate the Poisson ratio. So how we can do this? That is like the first one is about the problem is a resistance wire strain gauge uses a soft iron wire of small diameter. The gauge factor is 4.2. Neglecting the piezoresistive effects, calculate the Poisson ratio. So the formula is gauge factor, which is equal to 1 plus 2 nu plus del rho by rho divided by epsilon. So this is your piezoresistive effect, in the sense this whole factor, that is del rho by rho divided by epsilon, this will get cancelled. So you'll have gauge factor which is equal to 1 plus 2 nu. So from that, actually the question is you have to calculate the Poisson ratio. So if you are substituting those value, you will have nu which is equal to gauge factor minus 1 by 2. The gauge factor is plus 4.2. So after substitution, you will have the Poisson ratio value is 1.6. Okay, the next problem, that is the problem is here you have to denote if there is a compressive force, then you are supposed to apply the strain value negative. If it is tensile force, then you have to apply positive value. So in the question, a compressive force is applied to a structural member. The strain is 5 microsecond. So compressive force is applied. So you have to take the strain is minus 5 microsecond. Then two separate strain gauges are attached to the structural. One is nickel. So one is nickel wire, the another one is nichrome. For nickel wire, the value of gauge factor is minus 12.1 and the other one, the value is 2. And calculate the value of resistance of the gauge after they get strained. Resistance of strain gauge before being strained, it is 120. So before the strain value, the value is 120. So we are going to calculate if the wire is getting strained. So we know the formula del R, which is gauge factor into your strain into R. Okay, so here we are supposed to calculate the change in resistance. So the gauge factor, because of this is compressive, so we have to take the value minus 5. So minus 5 into 10 power minus 6. And 120 is what? Before strain, what is the value of my resistance? That is 120. Gauge factor is for nickel wire, it is minus 12.1. So when you are substituting this, you will have 7.26 milliohm. So the value is, I am getting positive. So I can just tell this is increasing nature. The second value, gauge factor is 2. So when you are substituting, you will have the value minus 1.2 into milliohm. So if it is minus, so it is going to decreasing nature. So increasing of this milliohm, that is 7.26 milliohm in the value of the resistance, decreasing 1.26 milliohm value of resistance. So in this question there are two complications. You have to find out whether they are given compressive or tensile, the first point. Then second point, what we are going to calculate, whether you are going for like a change in resistance or original resistance. That is very very important. Okay, so these type of problem they will ask in your strain gauge. Either they will ask Koch factor, or they will ask strain, or they will ask resistance, change in resistance, or length as well as change in length. So these are some of the different questions they can ask in your strain gauge concepts. So the another one concept I would like to tell you about, already we had a discussion on LVDT concept. I think you would have remember LVDT, which is nothing but again linear variable differential transformer, right? Or we can call linear variable differential transducer. And LVDT, here we have two secondary as well as one primary winding, right? Two secondary and one primary. And the working principle of this particular LVDT is mutual inductance. And the input of the LVDT is displacement, and that will be converted into output voltage. That is what your working nature of your LVDT, right? But these are the types like LVDT which comes under variable inductance type transducer. Variable inductance type transducer. So under variable inductance type we are having two. The first one is about variation of self-inductance. The next one is variation of mutual inductance. Then production of eddy current. Okay, so under variable inductance we are having three different types. First one is variation of self-inductance, variation of mutual, then production of eddy current. So under this heading, that is your variation of mutual, we had a discussion on LVDT, that is linear variable differential transformer or transducer. So what is that self-inductance of your coil? You all know in the 12th standard maybe you would have studied L, which is N square by R. That is your L is what? Self-inductance. N is number of turns, and this is what the factor we used to call reluctance. Reluctance of the magnetic circuit. Reluctance of the magnetic circuit. So what is that reluctance? Reluctance, which is like L divided by mu into A, and L is again number of the magnetic coil, how much amount of the length it is going to be. That is what your distance L, and moreover it is also depends on the L we used to call N square, that is number of turns mu into G. And here this mu, which is nothing but permeability of the medium. It is all related to your magnetic. So this is permeability of the medium. This is what your mu. And what is that G? G, which is nothing but the dimension, area divided by your length. And this particular topic, that is either you can go for variation of self-inductance or mutual or eddy current. These three different concepts where comes under variable inductance type. In the variable inductance type transducer, which is used for measuring displacement. So finally, after substitution of the whole component, the L, that is your self inductance, N square by R we used to prefer for measuring self inductance, that is number of turns of coil as well as the reluctance. So the output is change in voltage or change in inductance. So that is how we are going to measure by the use of your variable inductance type transducer. Either the concept is based on your variation of self-inductance, or it is variation of your mutual inductance, but all the things are these particular component, it also consisting of an coil, that is ferromagnetic coil. Then you'll have a target, so which position you are, and there will be an air gap will be there automatically. So when you are applying a displacement, there will be a movement. The output we have taken across this point here to here. So when this is core, the permanent magnet, and the coil is wounded around this portion. So this is your coil part. Then you have a core, that is ferromagnetic core. You have a ferromagnetic core, and these are all like an iron piece. Okay, so when the displacement is occur, then automatically there will be a deviation. Either this will go this direction or this direction. This distance will get varied. So from which we can able to calculate the output voltage across this portion. So here you have an air gap which was present in the target as well as your ferromagnetic core part. So the same L we can also measure using N square by the reluctance term. It is replaced by Ri plus 2 into R suffix G. That is this Ri, which is nothing but due to iron parts. This will happen, and this Rg, it's because of the reluctance of air gap. So using this we can able to calculate the value of your L. Okay, but here the important topic is your LVDT. That is very important. So this is what I would like to inform you related to your LVDT. And now we are going to discuss on the topic called smart sensor. So what is the meaning of smart sensor? So you all know from the word smart. So what is meant by smart? Something which is if it is an intelligent, right? The people we used to call, if the person is good in look, then we used to call he is a smart guy. So the same way in your sensor also there is a smart sensor, and smart sensor means it is nothing but the sensor is interface with the hardware, interfacing with the hardware with all the features. It's like the sensor which consists of, there is a particular facility like ranging, then it should have an calibration, everything should be in a single unit. Then there should be a decision making, so there is no need to go for the supporting part. So data collection, data displaying, all the nature together. That is the reason why this is called smart sensor. So in present situation, there is a topic called fusion, that is sensor fusion. Sensor fusion, which is nothing but at a time you will have only one unit. Using this particular sensor, you can able to measure the temperature, pressure, flow, level, likewise. So if a particular unit, a single unit which consists of all the nature, this is what actually fusion technology, that is the people used to call sensor fusion. So this is what comes under smart sensor. So how the block diagram of smart sensor we have, just I would like to show you. Maybe like this is the outer part of your sensor, and which consists of an amplifier. Then we have a signal conditioning unit. Signal conditioning unit. Then we have a memory part, that is your EEPROM, and which also consists of TED, which is nothing but transducer electronic data sheet. Transducer electronic data sheet. So these sections all together in one single block. So the whole thing we can call it as an interfacing module. We can call it as an interfacing module. Then not only that, it also consists of ADC, DSP. So these things comes under the processor. Then it also supported with an adjustments, offset adjustments, and temperature adjustments. Not only that, the same thing which consists of communication unit, that is nothing but modulation and demodulation, that also possible. And here we have an display unit. So bidirectional. Okay. So the features are like in your smart sensor, it is self-calibration. Then it also consisting of communication units. Then we have multi-sensing, that means multi-functions. Then we can have a linearization. These are some of the features of this particular smart sensor unit we have. Then TED, that is your transducer electronic data sheet, which consists of IEEE 4.1, 1451.4 standard. Then it also consists of EEPROM. Then it has its own, this particular data, your TED data will give you the serial number, then manufacturer details, then your measurement range, then what will be the sensitivity, that is the range of sensitivity. Then it will also give you model number. Then it will give you what was the conversion of data which was happened inside this particular unit conversion data, that is also we can able to get it. So what is your sensor? The sensor which consists of all the units. Amplifier, which is nothing but if the signal voltage is very few amount of millivolts, that can be increased by the use of your amplifier. Once the signal is getting amplified, there will be a feasibility of some noises will be there, so that can be removed by your signal conditioning unit. So the noise is getting removed by using filter or whatever the devices. You want to increase the amplitude, then we can go for signal conditioning. Not only that, you have an interfacing module, then that will be connected with your processor section. So analog is converted into digital, then you have a DSP processor, then that also connected with the offset adjustment and temperature adjustment. It also consists of all the display as well as memory unit. Then also it will interface with the communication module. So communication module in the sense, whatever the data you want to send it from the center to the receiver. You have a center and the receiver unit, and how we can able to send it, that is what your communication part will refers. So this is what all about your smart sensor. So the main thing is your block diagram. You have a sensor part, amplification, signal conditioning, EEPROM, ADC, DSP, processor, communication. And the smart sensor, you have an advantages, that is self-calibration, communication, multi-sensing and linearization. Not only that, you have an ranging, calibration, decision making and the data all together in a single unit. That is what call it as a smart sensor. Okay, thank you. So I think you would have understand the type of strain gauge, then problems, then what is variable reluctance, and what is about your smart sensor concepts. Okay, thank you so much.